So it's often easier to graph the reciprocal function right over top of the original function. I'm going to show you in example 3 how that would look and answer these questions. So we're given the linear function f of x equals 2x plus 4. So this is just a straight line. We're going to determine the reciprocal function. So we can do that right here. Reciprocal function called 1 over f of x means that we're putting a 1 over the 2x plus 4. So that's my reciprocal function. I don't want to call this f of x anymore because f of x describes the linear function. So you can just put a y equals. Determine the vertical asymptote. The vertical asymptote will be the NPV. So we would look at the denominator and we would find the 0 of that. So 2x, you can put a not equal to sign if you want within your work, but you do have to remember that when you're stating the asymptote itself, it's an equal to sign. So we're going to have an asymptote at x equals -2. So we're going to end up drawing that in here. Determine the x-intercepts and y-intercepts of f of x and y equals 1 over f of x. It's often good to make sure your intercepts are clearly plotted. So we want to show that here. So I'm going to just go down here for C. So we're going to find, so this will be for the linear graph. So we're going to find the x-intercept for the linear graph. So 0, let y equal 0. It's going to be the same math that we just did there, actually. So we can quickly get to x equals -2. For my y-intercept, you let x equal 0. You probably can recognize, so if you don't show your work on this and recognize that 2 times 0, that's just going to be 4, or the b value is the y-intercept. So you can jump directly into stating that as well. Let's do the x and y-intercepts for the reciprocal function now. So I want to show what would happen with the algebra. So when you let y equal 0, and you're going to cross multiply, so 0 times 0 is 0, 1 times 1 is 1. Well, 0 can't equal 1. You don't have a variable. This is going to happen every time. So you're going to start to realize you don't necessarily need to do the algebra to realize there is not going to be an x-intercept because you always have a horizontal asymptote at y equals 0 that we will end up drawing in. For the y-intercept, we're going to let x equals 0. So 1 over 2 times 0 plus 4. So we're going to get y equals 1/4. You're going to notice that the y-intercept will be the reciprocal of the y-intercept for the linear graph. So the reciprocal graph's y-intercept will be the reciprocal of this one. Okay, let's look at graphing the functions y equals f of x and y equals 1 over f of x. So I'm going to graph the linear function first. So I'm just going to use y equals mx plus b to graph my linear. So I'm going to plot my y-intercept, then I'm going to count my slope. So I need a scale on here. Make sure you put your scales in your work. So you're going to go up 4. This is going to be your y-intercept, and your slope is going to be 2. So you're going to go up 2, right 1. Now that's kind of off the page. I can still plot that point, but it might be a good idea to count down to left 1. So as long as you have a positive slope of 1, that's how you can extend your graph in this direction. So we're going to connect that. We also noticed, you notice that you have your x-intercept of -2. You could have used that instead of counting the slope and just plotted this, the intercepts, so -2, and you would have graphed that. So we're going to call this f of x. You can call it equals 2x plus 4, but you can just label it y equals f of x, which is what we're graphing. So I'll put the y equals in front to make that a little better. Okay, now I'm going to graph the reciprocal one. So what I'm going to do, I'm just going to switch to a red pen here so that it just stands out a little different. I'm going to label it anyway, but we're going to follow the rules that we've written at the top of this page. So the x-intercepts becomes the vertical asymptote. So where I have an x-intercept, it's the vertical asymptote, which we found here anyways, but it's still good to use this strategy. So a dashed line with arrowheads, label that asymptote at x equals -2. While I'm drawing the asymptotes, it's a good idea to remember that y equals 0 is also going to be one of the asymptotes, even if you draw it in at the end. But it's a good guide because we know that it's going to approach. We don't have an x-intercept, so we know the graph is going to approach the x-axis. Then what I'm going to do is I can plot my y-intercept. I know that's 1/4, but I'm going to use taking the reciprocal. I want to make sure I plot my invariant points. So where y equals 1, so this is where y equals 1 here, even though that wasn't a point I originally graphed, this point does not change. Where y equals -1, This point doesn't change. So I'm putting a point right over top of the original graph. Now I'm going to take the reciprocal of any y value. So 2 becomes 1/2. 4 becomes 1/4, which is my y-intercept of 1/4. So that's enough points to go along here. This is really sort of squeezed in here. You could kind of see where y equals 1/2 becomes 2. Otherwise, you can just have it approach the x, or the asymptote rather, and you'll have enough of a guide on what shape this is going to become. Same thing down here. We have 1 point, but -2 becomes -1/2. -4 becomes -1/4. We know this approaches the asymptote, or you can look at the halfway. So where y would equal -1/2 becomes -2. So you're always going to get this split graph shape with linear. Now there's still key points that have to be drawn. Your intercepts, I'm checking to see that these points are drawn in. Your invariant points must be drawn in. So you can't just draw, a split graph and just hope that it goes through everything. Now, because I have both graphs on here, I must label. So this is the 1 over f of x graph. Okay, so you're always going to get that split graph if you've got it is always going to be the reciprocal of a linear function. So a linear graph. I'll just say function underneath here. So you're always going to have a split graph shape for a linear function.